I've got a flat board just sitting here pretty much level with the earth. This is a 3-inch piece of aluminum, solid rod. It's 4 inches long, 3 inches in diameter or circumference. And I put a red line across to show a center line. If you understand my theory, and you probably don't, I say there's a static charge in the ether. There's particles vibrating that are the wrong frequency and wrong size to come together and form mass. But the universe is completely jam-packed with these particles that are vibrating. Only the ones that vibrate at the right frequency, the golden number frequency, pull together to form mass. And as these little particles that are at the right frequency combine and bundle and compile, the other particles that are individuals that can't form mass have to feed them their electrostatic charge because they're now vibrating as one big unit. Since they're all vibrating at the same frequency, when they touch, they're getting bigger. They're all collecting and making one big vibration at that frequency. And as that charge comes in, you get 4 of these balls of how many thousands of them particles, of good vibration particles, you get 4 quarks. That charge comes in, it energizes 1 quark full of balls, and it pulls the other 3 to it. Then it energizes number 2, pulls the other 3 to it, then energizes number 3, pulls the other 3 to it, and number 4 and the other 3 to it, and it goes around in a cycle at the speed of light. It's an electron. It's not orbiting, it's an illusion. It's the static charge moving around it so fast, electrostatic bonding, almost an electromagnetic bonding of these 4 quarks. Anyway, everything of mass in the universe experiences this static charge coming into it. That's your beginnings of gravity. The earth is experiencing it. All celestial bodies experience this gravity. That's what gravity is, the static charge coming in and giving the strong force to protons via the electron functions. Now there's such a massive amount of that going into the earth that it pulls things, this little stuff on top, towards it. It pulls on the moon too, but that's a different part of the realm. This I want to explain now is gravity here on earth. So this static charge is coming down at a specific rate. I don't know the numbers for terminal velocity. You can look them up. But just like this 1-inch aluminum bar, the speed that the earth is pulling it in is that fast. Or even with this hollow tube, that's how fast that static charge is coming into the earth. This is the way my theory explains the strong force and gravity, magnetism, energy, all of it. So what I have here is these little wooden sticks with electric charges drawn on them. This is the static charge coming in to the earth. It's basically on a flat plane. There's a magnetic core in the center of the earth that makes a magnetic field around the earth. This might be tilted a little bit, but not enough for us to feel it or to notice it. It's negligible. So as this static charge comes in, it's going through everything on the surface to get to Mother Earth. Well, for us, and this piece of aluminum, to hold itself together, it's stealing part of that. That's why it's pulled to the earth. As the static charge goes through this, Mother Earth pulls in a huge amount more, especially in this area right here around this aluminum bar. Mother Earth is pulling in so much, it pulls it right through this. Well, this is stealing part of that for its atoms to hold itself together. That's why this is pulled down. That's why everything is pulled down. What I want to show, and I'm going to use this 3-inch aluminum rod to do so. I'm trying to keep my center line straight. Keeps wanting to move on me. But it doesn't matter. This static charge is coming down into the earth everywhere. It's saturated. The static charge is saturated everywhere in the universe, but it's saturated coming through mass to get to the core of the mass. And it's going through this, mainly all the way around it to the center, but it's going mainly down through as it does that. And as it does that, it's saturated all the way through. And next I'm going to show you some lines on here to kind of give you an idea of the angles of what it's doing as it comes in. And we'll move on and do that now. Okay, now I've drawn lines on this to show you the static charge is saturating everything, but these are just to show you generally, you see how it's going. The static charge is coming in and it's hitting all these lines, but it's actually saturating it completely through it. I mean, every in between the molecules of it, in between the atoms of it, this is moving towards Mother Earth. This is stealing part of that to use its own electron functions, but as that theft happens, as the rest of the flow goes by, it's dragging it with it. That is gravity. If you don't understand the beginning parts of this, you have to check out my theory, The Good Vibrations, copyrighted, of course. So as this charge comes in, that's what holds that there. Like I showed you, that's when things drop. That's what causes us, our feet, to be pulled to Mother Earth. And I'm using these lines, which I'm going to show you in a minute, is why, to give us a little calculation to see what the minuscule problems this causes when we take this flat plane and we're going to tilt it down and put an angle to it. We're going to give it a hill. We're going to put some angle to this surface that this is lying on, and I'm going to show you why it rolls downhill. And after that, we'll get into some more things of why this rolls downhill, why this and hollow things have a different speed of rate of roll, and why their mass does what it does. But so that's this part. The static charge is coming in, but you can see, but it's just saturated all the way through this, but the lines are giving us an idea of how to kind of calculate so you can see the difference when this is on a hill. And we'll move on to putting this on a hill, and we'll do that now. Okay, now what I'm going to show you is if I put our center line, and I may not be perfect here, vertical, you see how the first line is touching the wood. And the first line over here, and this isn't perfect, and it doesn't have to be. You can move this line in equal to that one, but it wouldn't be touching the wood. There's a gap there. I'm going to show this in more detail in a moment. But our static charge is still coming in straight. Let me stop them from swinging. It's still coming in straight. It's not coming in, angled. And it still stays straight, even though I angle the back board here, see? The static charge doesn't give a shit about the angle of a pill. It still comes down straight. So it's coming in straight down these lines. And it's saturating the whole thing, but I'm showing the lines to give you an idea of my point. So our static charge still coming in straight, even though this is on a tilted plane. And if you notice, if I put the square 90 degrees and I keep my lines fairly straight, it's not straight, and I can draw another line to show you, but you see it covers part of that line and not all the lines. It cuts across at an angle, at an angle like that, because that's what this angle is. But our static charge is still coming in with these red lines straight down to Mother Earth. Gravity's still pulling this straight into Mother Earth. So I wanted to show you that so you would understand that what I'm going to show you next in a more close-up view is I'm going to zoom in on this more and show you this point here when this round bar is resting on an angled surface, a hill. I'm going to show you why gravity causes it to roll downhill. The Earth isn't pulling it down. The static charge is pushing it down. Now, the fact that the Earth has more atoms and denser atoms altogether than this little piece of aluminum causes it to pull it, but it's because it's pulling more static charge. But the static charge is actually pushing itself into Mother Earth to feed her, and Mother Earth is pulling. That is true. But it's a static charge going through this is what causes gravity. And that's what I want to show next. And we'll move on to that. Okay, I want to backtrack a little bit here. We got this on a solid plane, a flat plane, straight up with the world. You just have to take my word for it. The lines on this are pretty well straight up and down, level. And I've got my two boards. I got a little board here on top, the bigger one, which we're going to do the angles again here in a minute. But what I want to show is with my square, this is just a square, with this laid up against, if you notice, each line is pretty well straight. I may have a little bit of turn on my piece of aluminum. And I'm trying to get it straight where it'll sit there. Pretty straight. See, each line's pretty straight. I mean, it's a little off, but... And each line is fairly straight. But the point of this... Pardon my cold. I'm out here in damp garage in my shop again, my lab, whatever you want to call it. I know these lines are not perfectly separated. They're different. But if you notice, our gap here and our gap here equally from the center line is equal. That's why it doesn't roll. It just sits there. Because the static charge is coming down through this whole thing equally from the center lines out, and it doesn't need to twist it. There's no twist. It's pulling straight down on both sides, equal. And so there's no bigger gap here than there is over here. If these lines were equal, there's no bigger gap on either side. Okay, that's why it doesn't roll. And the numbers they have that's been configured for the size of the mass and how big it is and when you put it on an angle, I have no dispute with that. Because if you put this on a different planet, like the moon or on Jupiter or something with different gravitational properties, all of the things I'm going to show you will change. And their numbers for correcting that or adjusting for that will change too. And I have no discrepancy with that. What I'm trying to show is why this does this anywhere in the universe. I'm just trying to show why this does this. I don't dispute the numbers of gravitational pull because of mass. I'm trying to explain why gravity works. Okay, so we're on a flat plane, and like I said, I'm sorry my lines are not straight. If they were, if you notice, the gap would be equal on either side from center. If you go out so far from center on this side, you have such a gap. If you go out from the center on this side equally, you have the equal gap. The gap is equal because we're level, and you have to take my word for it. But we're level, or it would roll, right? Okay, kind of obvious. But what I wanted to show here is when you start taking that angle, and I'm trying to use a block, and I'm going to angle that top board a little bit. If you notice, I've got an angle now. And what I want to show in a little bit of an angle here, before we move on to the next part, you'll see this again, is I'm still straight with the world, level with my lines. This line is real close to the wood. This line is farther away. And if the lines were equal, you would see there's more of a gap on the side down here on the lower side of the angle. And I'll increase the angle and try and show you what I'm talking about. Now, if I increase it to there, do you see the difference? Now, my lines are straight. Gravity's coming down straight, so it's going to want to try and balance. But it can't, because as it balances there, the lines keep moving. They keep moving, they keep moving, they keep moving. And I'm not disputing on the planet Earth how much mass is here, how big it is. The numbers that make this roll at a certain speed or a certain time or certain much, or amount, is or what the numbers are. What I'm saying, the reason it does it is because this pull down on the gap side is much more on where there's a gap. The static charge is pulling equally through this. Over here, we're touching. Over here, we are not. I have to do this in an extreme angle to show you. If I move this down, you can see. Let me back up. The center line is the center line, right through the middle here. That's the center line. But look at the other lines, out here and over here. Look at the difference in the gap. It's a major difference in the gap. Let me set this up where it stays so I can use both hands again. I'll pull this back a little bit. The bottom board here is with the earth. It's level, right? Take my word for it. It's pretty much level with the earth. Now I'm going to level that center line of where gravity's coming through this entire mass straight down with my square. There it is. Right there. I'm holding it steady. If you notice, we're touching here and we're not touching here. And even if I move this line in, equal to that one, we're touching here and we're not touching here. So it's going to try and balance it. When it rolls, to balance it, it's still not right. Because look, we're not straight anymore. This straight line is now going to move with my bottom board to there. Look at that. It's out of whack. So I have to, forgive me, I have to twist this center line this way with my bottom board straight through the center of the piece of mass. If you notice now, it's off angle. That much. Look how much we're off angle. Because I've rolled to where these two lines are equal like they were on a flat plane. And then it will try and balance this way. And if you look now, look how far off I am center. And it stays the same all the way down past center. And like I said, the numbers are always right. I'm just trying to show you why the numbers do what they do. It's that gap. The static charge coming through, there's a gap here. It tries to center. It can't. It keeps, there's more angle. Center, 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 center. The only time it centers is when it hits another flat surface as such, and then it centers. See, it centers because it's equal on both sides past center. It's equal this side, past center. So I wanted to show that. And I also understand the numbers are also correct for not just round things, but if I set it this way, the angle that I would have to tip this board to make this thing slide, it tips before it slides because of the height, the angle of the mass on top is going to push over. Same thing, different application. Watch, before it slides, it basically tips. However, if I shorten it to a shorter piece and tip it, it slides. It doesn't tip because your mass is down here. And they've got their numbers figured out for why this does that, because of the size of the mass, the friction that this flat surface and this flat surface will cause, and what it takes, here we go, to make it slide. You know, glass to glass will slide quicker than metal to wood or metal to metal, and so forth and so on. Depends on the surface. My point is, it's gravity. And what gravity is that static charge coming through everything down to the bigger mass of the earth. And I'm using the earth as my example. When you're balanced here, it sits. As soon as you throw these gaps out of balance, you get, I put my hand there, you get roll. I just picked it up a little bit. As soon as you throw those two gaps out of balance, I'm not touching it, it's sitting there, pretty vertical. May not be perfect, but close enough. I'm gonna lift the board now. As soon as I lift the board, that gap over here is going to get bigger. And it says, hey, let's fix that. Let's fix it, fix it, fix it, fix it until we're flat again. And then it says, hey, we fixed it. It's fixed now. It's just automatic. Anyway, that's what I wanted to show you here. I have no discrepancy for the numbers of how this happens, but I'm just trying to show you why this happens. And we'll move on. Okay, I've got another little board, this little thinner one, smaller one, resting on top of our original, angled plane board here. We'll use this other board again, this bottom one, in a moment. But right now I want to use this little one to show you something. So here's our aluminum piece, and my lines are straight up with the world, level. I'm not tilted with the plane of the wood, I'm level. And I can take this little thin piece of cardboard and shim it, and it won't roll. Now, if I take the shim out, of course, it's going to roll. But the point is, if you notice, that shim is taking up some of the space. And my shim's smashing on me. But it's taking up that space that's a gap. And if you notice, I don't know if I'm close enough, there's a gap here where there's not here. So as our static charge comes through, it can push down here. It's like it's pushing on this mass, dragging it to Mother Earth, or the static charge is pushing itself down. It can push down on this side because it's hitting the wood, but it can't on this side. So it tries to equalize that. And as it does to roll there to equalize it, well, look, now this line's not touching, but this one is. So let's move to another line. This line's touching, But now this one isn't. And it keeps trying to catch up. Do you understand? That gap of the static charge coming through just that little bit here, pulling on all these, is not enough. Now it's pulling on this side too, but that balance of over here where it's coming down is not enough. That is not enough counterbalance where it's touching the wood to counterbalance this because of the angle. As it's pushing down, it's going to force it that way. It's going to go that way. It wants to roll. It's going to pull it over like so. It's not going to roll uphill. It's going to roll downhill. It's that gap. Because you notice when it was on a level plane, it didn't roll. It just sat there because the gap was equal on both sides. As the static charge went through, it would balance itself on either side of center line. Well, now we're out of balance. Over here, we've got connection. Over here, we do not. So it wants to balance that. It wants to twist this to balance it. So we'll twist it and balance it. But now we're still out of balance. So it's going to twist some more. And it keeps twisting, trying to balance. It can't until it rolls to a level plane. Then it can balance again. Unless this was soft and you can make a dimple. Or you can take a cardboard and shim it. But do you see that? That gap of the static charge coming through and pulling down is going to make this side roll because there's not enough counterbalance on this side. It's just not counterbalanced. Okay, I have several different cylindrical items here. On the ones on your right here are solid, and the ones on the left are hollow, as you can see. 3-inch solid, 2.5-inch solid, 1-inch solid, 1-inch solid, and a 1/4-inch solid. Over here, I have a 2.5-inch hollow, 2-inch hollow, 1-inch hollow, and a 1/2-inch hollow. This black tube may be hard for you to see because I've painted it black. I want to show you the difference in the speed that they make it down this hill, no matter the size, but it depends on whether they're solid or hollow. Okay? Very simple. So we'll take the 3-inch solid and we'll go with the 1-inch solid. 2 solids. And I've got a little bar here I use for my marker, so they go at the same time. So the 3 inches back here, the 1 inch is closest to you. Now watch when they roll down and see which one hits first, and I'll count it off. 1, 2, 3. Same time, right? I guess you saw that. And we'll do it again just so you see. 1, 2, 3. Basically the same time. My bar may be a little crooked, but basically the same time. So a 3-inch solid bar and a 1-inch solid bar went the same time. So let's take 2 1-inch solids. This one's aluminum, it's pretty heavy. And this one's graphite, it's real light. So we'll try these 2 solids. The aluminum's over here away from you, the graphite's closest to you. And 1, 2, 3. Basically the same time. I'm not going to do that one again. And I'm going to take the little aluminum and this little copper rod, 1/4 inch to 1 inch. 1 inch back here, aluminum, 1/4 inch copper closest to you. Ready? 1, 2, 3. This was just a little bit behind. Look how small it is. A little bit behind. I'm going to run that again. 1, 2, 3. Same time. That's the way I let go of it. I'll do it one more time. 1, 2, 3. Just a tad bit behind. I can live with that. Now what I want to show you is something weird. I'm going to take a 2.5-inch aluminum solid bar rod and a 2.5-inch hollow tube rod tube. I'm going to put the solid one back here, the hollow one up here, same size, but one's solid and one's hollow. Ready? 1, 2, 3. The aluminum beat. And I'll do that again to show you. 1, 2, 3. The aluminum beat. And in a minute, I'm going to show you why. But even more incredible, to prove this point, if I take the small 1-inch tube, and let's just go with the 3-inch solid, which one do you think is going to get down there first? Let's see. 3-inch solid aluminum against a 1-inch hollow PVC. 1, 2, 3. The solid one made it first. I'll do this one again. And I'm going to change up some more just so you see. Same one again. 1, 2, 3. The big solid one made it first. Okay, it's bigger, it's heavier. I believe it. So we'll go 1-inch to 1-inch. 1-inch solid aluminum to 1-inch hollow PVC. Got the aluminum back here and the PVC closest to you. 1, 2, 3. The 1-inch, the solid, beat the hollow. And we'll do that again. Solid's back here, hollow's closest to you. Watch again. 1, 2, 3. The solid beat the hollow. And I can do any combination you want. Great big heavy one, little bitty hollow one. Heavy one away, hollow one closest to you, half-inch hollow PVC, 3-inch solid aluminum. 1, 2, 3. The aluminum bead. Okay, we'll say that's heavier, that's why. And I'm going to show you something else. If I take, let's take the biggest tube I have and the smallest solid I have. So I've got a 2.5-inch hollow tube of PVC and a 1-inch or 1/4-inch solid piece of brass. I'll put the brass closest to you and the PVC over here, and we'll race these two. One solid, one's hollow. 1, 2, 3. Oh my God. In that instance, the hollow one beat. Look at the differential. Look at the differential. That's why. That's why I put this one in here. If it's small enough, it will get behind. But let's do this again with the 1-inch aluminum solid and the 2.5-inch hollow. Which one's going to beat now? It's quite a bit bigger than the brass or the copper solid. The 1-inch is, but we're going against the same one. Copper beat. So I'll put the hollow over here and the solid closest to you so you can see the bigger one on the back side. And 1, 2, 3. Oh, beat it by a mile. Beat it by a mile. And we'll do that one again. 1, 2, 3. Beat it by a mile. Those two, this little solid aluminum beat that big tube. If you noticed, all the solids pretty much beat the hollows. All the solid ones beat the hollow ones in pretty much every instance. The only time they didn't is because this little itty bitty guy. He really took a lot to go. But when you take things of equal size and even of unequal or equal mass, you get the same result. That's why I wanted to show the PVC and aluminum, both the same size. I'm going to run this one again. Aluminum over here, farthest away, PVC closest. They're the same diameter. Same diameter. The aluminum will beat it. And other than something being extremely small, to where it takes a long time for it to make revolutions, that will get behind. And that I wanted to show that. But when you take things proportionally close, or even remotely close, look at the difference between these two. And we'll do them again, just to show you. Look at the difference in diameter, how long it takes it to go around, and how long it takes it to go around. And we'll do these again. 2.5-inch PVC, 1-inch hollow PVC, and 1-inch solid aluminum. And we'll do them one more time. 1, 2, 3. The aluminum beat. So on most every instance, the solids beat the hollows. The only instance that doesn't work is with this little bitty copper rod. It will get behind some of these hollow ones. And we'll just run the solid copper 1/4 inch against the 1/2 inch hollow PVC. Let's run these two. I don't think we've done that yet. PVC away from you and the copper towards you because the copper's smaller. And we'll run these. 1, 2, 3. You see that? The copper beat the hollow 1/2 inch PVC. The solid beat this big hollow one. We'll run that again. 1, 2, 3. It beat it by a good bit. And like I said, if I put the copper up against a 2-inch aluminum tube, results a little bit different. 1, 2, 3. They're about the same time. Then I can do that one again. 1, 2, 3. And the brass is actually, the little one's a little bit quicker on this one. And it should be because it's solid. But as you noticed, it just depends whether it's solid or hollow. 1/4 inch brass solid or 1/4 inch copper solid against 2.5 inch hollow PVC. 1, 2, 3. Almost the same time. I'll try it again just so it's not. 1, 2, 3. About the same time on those two. But this little guy kept up with this big guy because of the difference in mass from center out. This only has this out here, that has it all the way around. Now I'm going to show you next is why the solid cylinders always beat, almost always, except for this little guy. These always beat. I'm sorry, this is hollow. The solid ones, no matter how I mix match them up, the solid ones beat the hollow ones down the hill. Next, I'm going to show you how my theory explains why. And we'll move on to that. Okay, now I want to show you why the solid masses always beat the hollow masses rolling down this hill. And it's my theory. It's the same thing. My theory shows the same thing. The difference is the solid mass has all the static charge getting drug. It's getting stolen through all this mass here inside this, even on the back side, but on the front side especially. Look at all that mass that's stealing electron functions. It's stealing static charge, all these atoms through this whole cylinder. All this is stealing. But here you don't have that much theft. There's nothing in there. The air is not stealing for the metal. The air steals for itself, and it has its own problem when this rolls. And that's what causes the air to tumble. My point, this is stealing so much more. And if these two were equal, it'd be the same. I'm just using these two because I already had lines on this one. And I don't have a solid one this particular size, and I don't have two aluminum pieces, one hollow and one solid, that are the same exact size. But this still shows the same thing. Even a smaller aluminum, the 1 inch, beat this down the hill. And the reason why is because the solid ones are stealing all through here, all the way down to Mother Earth. But if you look here, the theft is only here, 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 down through here, where these lines are. And it goes through the air differently than it does the metal, for one thing. The second thing is the air doesn't make resistance in the aluminum, and it doesn't stop it from rolling, and it doesn't give it push in here, not like this solid does. So you've got more static charge pulling down on our gap on this than you do on the gap on this. Look at that little bit of pull right there on the gap through this side of this thin lip. and you've only got this much pulling back. So it's balanced, but it's the same balance for itself as this is. It's going to roll because of the gap, the balance that I showed you earlier. But the reason that the hollow ones are always slower is because they don't have near the static charge pulling down on this front side. The air does not count. It's not helping it. It's not helping it. It's really not hindering it when you compare these two together. This is always going to beat that. A solid mass will beat the hollow mass. I showed you that with rolling the different masses, hollow and solid, down this slope. This is why. This is how my theory holds true. It's pulling down on more of this, and it goes faster because it's got more to grab. It's grabbing. The static charge is grabbing as it goes down more on this than it is on something hollow. Hope you get that. I hope you get that. Good vibrations, copyrighted. Thanks for watching.